So let's talk about a special type of vector field called a conservative vector field. A vector field is called conservative on a given region if it could be written as the gradient of a scalar function. And if you'll recall, the gradient of a scalar function has the expression partial x phi, partial y phi, partial z phi. Okay? So if you could take some scalar function, sometimes called a scalar field or scalar function, and you take its gradient, okay? If a vector field can be written as the gradient of some scalar function, it's called conservative there. And you could think about that phi as something like an antiderivative of the vector field, okay? If you could think about it in that rough way. Okay, so you're given a vector field and you want to know if it's conservative. How do you do that? Before we jump into that, we need some definitions of special types of regions. A region is called connected if you could connect any 2 points on R, at least in this sort of simple sense of what we're using. And it's called simply connected if every closed simple curve in R can be deformed and contracted to a point in R. Okay, and let's just take a closer look at that. So this region here is connected. You could connect any 2 points, and it's simply connected. And frankly, the best way to think about simply connected for our purposes is that the region doesn't have a hole. Okay, if the region had a hole in it, then you won't be able. So let's take a look at this next example here. This region is connected but not simply connected. And let's take a look at a curve that a simple curve that couldn't be deformed and contracted to a point. So if you had this curve here, okay, you can't contract it to a point. It'll get smaller and smaller, but that hole that you see in the middle will prevent it from contracting to a tiny point. Whereas for the region that we looked at here, okay, that won't happen. You would be able to take that curve and contract it ever smaller into a point. This region here is not connected. You can't connect a point here to a point here, okay, but it is simply connected because any curve that you draw in there can be contracted to a point. And this region here is neither connected nor simply connected. So with those definitions, we could develop a test for when a vector field is conservative. So on a connected and simply connected region, okay, a vector field in R3 is conservative if and only if its curl is 0. For vector fields in R2, a vector field is conservative if its curl equals, its 2D curl equals 0 on a connected and simply connected region. Okay, put simply, any irrotational field in a connected and simply connected region is conservative. Let's take a quick example here. We want to determine whether these vector fields are conservative on R2 and R3. Okay? Now, R2 and R3 are connected and simply connected, so we don't have to worry about that formality. And by the way, the only times that you would have to worry about that for our simpler purposes is, say you have some vector field K, and say it's given as, you know, this expression here. Okay? Well, if you'll notice, this is dividing by this square root of x squared plus y squared, and so the domain would have to be the plane not including, okay, so that symbol there means not including the origin. Okay, and so you have a hole right in the middle at the origin. Okay, for situations where you don't run into that sort of problem, okay, and you're just on R2 and R3, then you just need to check the curl. So let's go ahead and check the curl. Well, for A, our vector field F is in R2, So we use the 2D curl, which is defined this way. And we just plug and chug here. We're plugging in the y component here and taking the derivative with respect to x, subtracting out the x component after we take the derivative with respect to y, and we get 0. It's 0 on R2. R2 is simply connected and connected. Therefore what? Therefore this vector field F is conservative. G is in R3, so we have to take the curl. And we take the curl this way in R3. We get the expression that you see there, and we get 0, and therefore G is also conservative. Okay, since R3 is connected and simply connected.